Look up at the night sky. Every photon of starlight that reaches your eye has traveled for years, sometimes millions of years, to get here. But rewind time far enough, and you'll reach a moment when none of those stars existed. No galaxies, no atoms, no space, no time, just nothing. Or was it? The question of how our universe burst into existence from apparent nothingness is one of the most profound mysteries in all of science. And here's what makes it even more fascinating. We're actually starting to figure it out. 13.8 billion years ago, everything you see around you, everything that ever was or ever will be, existed in a space smaller than a single atom. The entire observable universe, with its 2 trillion galaxies, was compressed into a volume billions upon billions of times smaller than the period at the end of the sentence. Then it exploded. We call it the Big Bang, though that's a terrible name. It wasn't an explosion in space. It was an explosion of space itself. But here's where it gets weird. Really weird. Because before that moment, there was no before. Time itself began with the Big Bang. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because the framework that would give it meaning doesn't exist yet. So how do we know any of this? Well, the universe left us clues. Lots of them. In 1929, Edwin Hubble made one of the most important discoveries in human history. He pointed his telescope at distant galaxies and noticed something shocking. They were all moving away from us. And the farther away they were, the faster they were receding. It was as if the universe itself was expanding, carrying galaxies along like raisins in rising bread dough. If the universe is getting bigger, then logically it must have been smaller in the past. Much smaller. Run the clock back far enough, and you arrive at that impossibly dense point where everything began. But the real smoking gun came later. In 1964, 2 radio astronomers named Arno Penzias and Robert Wilson were trying to eliminate static from their antenna. No matter what they did, they couldn't get rid of this persistent hiss. It came from every direction in the sky, uniform and unchanging. They'd accidentally discovered the cosmic microwave background radiation, the afterglow of the Big Bang itself. This is ancient light, stretched and cooled over billions of years, but still detectable. It's the oldest thing we can see, a baby picture of the universe when it was just 380,000 years old. To put that in perspective, if the universe were a person living to 80 years old, this photograph was taken when they were just 14 hours old. That radiation tells us an incredible story. When we map it with extreme precision, we see tiny fluctuations, regions that were slightly hotter and slightly cooler than average. These weren't random. They were the seeds of everything that came after. Those slightly denser regions had a little more gravity, which pulled in more matter, which increased gravity further, in a cosmic feedback loop that eventually formed the first stars, the first galaxies, and ultimately you. But let's go back to that original question. How did something come from nothing? This is where quantum mechanics crashes into cosmology, and the results are mind-bending. In quantum mechanics, nothing is never truly empty. Even in the perfect vacuum of space, particles and antiparticles constantly pop into existence and annihilate each other in tiny fractions of a second. This isn't speculation. We've measured it. The vacuum of space actually has energy, and that energy creates virtual particles all the time. We call these quantum fluctuations, and they're as real as anything else in physics. Now, here's the wild part. Some physicists believe the entire universe might be the ultimate quantum fluctuation. A tiny bubble of space-time that fluctuated into existence and then, instead of collapsing back into nothing, inflated at an extraordinary rate. This brings us to inflation theory, proposed by physicist Alan Guth in 1980. According to inflation, in the first tiny fraction of a second after the Big Bang, specifically from about 10 to the minus 36 seconds to 10 to the minus 32 seconds after time began, the universe expanded faster than the speed of light. Don't worry, that doesn't violate Einstein's rules. Nothing can move through space faster than light, but space itself can expand as fast as it wants. During inflation, the universe doubled in size about 90 times in less than a trillionth of a trillionth of a trillionth of a second. A region smaller than an atom ballooned to larger than a galaxy. It's hard to wrap your mind around that kind of expansion, so let me give you an analogy. Imagine a coin the size of a quarter. Now inflate it using the same expansion rate as cosmic inflation. By the time you're done, that quarter would be thousands of times larger than the entire observable universe today. That's how violent and rapid inflation was. Why did this happen? The leading explanation involves something called the inflaton field, a hypothetical quantum field that permeated space in those early moments. Like a ball rolling down a hill, the inflaton field was in a high-energy state and wanted to drop to a lower energy state. As it did, it released enormous amounts of energy that drove the expansion. When the inflaton field finally settled, that energy converted into matter and radiation, filling the universe with particles. This is what we call reheating, the moment when the universe transformed from an empty, rapidly expanding void into a hot, dense plasma full of fundamental particles. But where did the inflaton field come from? Where did the quantum vacuum come from? Where did the laws of physics themselves come from? These are the questions that keep cosmologists awake at night, and they've led to some truly radical ideas. One possibility is that our universe isn't alone. The multiverse hypothesis suggests that what we call the universe is just one bubble among countless others, each potentially having different physical laws, different constants, different dimensions. In this view, universes are constantly being created through quantum fluctuations, each one inflating into its own separate reality. We just happen to exist in one where the conditions were right for stars, planets, and eventually life. Another approach comes from quantum cosmology, which tries to describe the birth of the universe using the same mathematics we use for subatomic particles. In this framework, the universe doesn't have a beginning in the traditional sense. Instead, time itself becomes fuzzy near the Big Bang, blurred by quantum uncertainty. Stephen Hawking proposed that if you go back far enough, time gradually becomes more and more like space, smoothly transitioning without any sharp boundary. In his words, asking what came before the Big Bang is like asking what's south of the South Pole. There is no south of the South Pole. It's not that there's a wall or a barrier. The question itself is meaningless. Then there's the more philosophical interpretation from physicist Lawrence Krauss and others who argue that quantum field theory changes what we mean by nothing. In classical physics, nothing means the complete absence of everything. No matter, no energy, no space, no time. But in quantum physics, nothing means the quantum vacuum, which isn't actually empty. It has energy. It has structure. It follows laws. In this sense, they argue the universe didn't come from absolute philosophical nothingness. It came from the quantum vacuum, which is the closest thing to nothing that physics allows. But does that just push the problem back a step? If the universe came from a quantum vacuum, where did the quantum vacuum come from? Where did the laws of quantum mechanics come from? Some physicists think these might be the wrong questions. Maybe the laws of physics don't come from anywhere. Maybe they just are, in the same way that mathematical truths just are. 2 + 2 = 4 not because someone decreed it, but because that's the nature of mathematical reality. Perhaps the laws of physics are similarly fundamental, existing not because they were created, but because they couldn't be any other way. This connects to something called the anthropic principle. Look at the fundamental constants of nature: the strength of gravity, the mass of the electron, the speed of light. If any of these values were even slightly different, stars wouldn't form, atoms wouldn't be stable, and life as we know it couldn't exist. Some people see this as evidence of design. But another interpretation is that we exist in this particular universe with these particular laws precisely because they're the ones that allow us to exist. In a multiverse with countless bubble universes, each with different laws, we necessarily find ourselves in one where the conditions support life. It's a selection effect. We're not special. We're just lucky. Now, let's talk about what the universe was actually like in those first moments. At 1 second after the Big Bang, the universe was about 10 billion degrees Celsius. That's hot enough to prevent even atomic nuclei from forming. The universe was a seething plasma of quarks, electrons, neutrinos, and photons, all colliding with tremendous energy. There was no matter as we know it, just a soup of fundamental particles. By the time the universe was 3 minutes old, it had cooled enough for protons and neutrons to stick together, forming the first atomic nuclei, mostly hydrogen and helium with trace amounts of lithium. This process, called Big Bang nucleosynthesis, predicted the exact ratios of these elements we see in the universe today, which is one of the strongest pieces of evidence for the Big Bang theory. But the universe was still too hot for atoms. Free electrons scattered photons constantly, making the universe opaque, like being inside a cloud. Light couldn't travel freely. Then, at 380,000 years after the Big Bang, something magical happened. The universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Suddenly, photons could travel freely through space. The universe became transparent. Those photons are what we now detect as the cosmic microwave background radiation. They've been traveling through space for over 13 billion years, growing cooler and more stretched with each passing moment as the universe expands. For the next several hundred million years, the universe entered what we call the cosmic dark ages. Stars hadn't formed yet. There was no light except the fading glow of the Big Bang. The universe was filled with neutral hydrogen gas, cold and dark, lit only by that dimming primordial radiation. Then gravity began to work its magic. Those tiny density fluctuations we see in the cosmic microwave background became amplified over time. Denser regions pulled in more matter. The first clouds of hydrogen began to collapse. And finally, about 200 million years after the Big Bang, the first stars ignited. These weren't like our sun. They were massive, hundreds of times the mass of our sun, burning blue-hot and furiously bright. They lived fast and died young, exploding as supernovae within just a few million years. But in their cores, they forged new elements: carbon, oxygen, iron, gold. When they exploded, they scattered these elements across space, enriching the cosmos with the raw materials for planets and eventually, life. The first galaxies assembled from these early stars, gradually growing larger through mergers and collisions. The universe began to take on structure. Galaxies, clusters of galaxies, superclusters, separated by vast cosmic voids. If you could see the large-scale structure of the universe, it would look like a cosmic web, with galaxies strung along filaments of dark matter like beads on threads. Speaking of dark matter, here's another mystery wrapped inside the origin story. When we measure the total mass of the universe using gravity, we get a number that's about 6 times larger than what we can account for with ordinary matter. Stars, planets, gas, dust, all the atoms in the periodic table, they only make up about 15% of the total matter in the universe. The rest is something else, something invisible, something that doesn't interact with light. We call it dark matter, and we still don't know what it is. But we know it's there because of its gravitational effects. In fact, without dark matter, galaxies wouldn't have formed at all. Those early density fluctuations wouldn't have been strong enough to overcome the expansion of the universe and collapse into the structures we see today. But wait, it gets even stranger. In 1998, astronomers studying distant supernovae made a shocking discovery. They expected to find that the expansion of the universe was slowing down due to gravity. Instead, they found the opposite. The expansion is speeding up. Something is pushing the universe apart, acting like anti-gravity. We call this dark energy, and it makes up about 68% of the total energy content of the universe. So let me break down the cosmic pie. Ordinary matter, everything we can see and touch, makes up about 5%. Dark matter accounts for about 27%. And dark energy comprises the remaining 68%. In other words, 95% of the universe is made of stuff we don't understand. We've named it, we've measured its effects, but we have no idea what it actually is. Dark energy is particularly bizarre because it doesn't dilute as the universe expands. As space grows, you'd expect energy density to decrease, like spreading a fixed amount of matter across a larger volume. But dark energy seems to be a property of space itself. As more space is created through expansion, more dark energy appears. This means that eventually, billions of years from now, dark energy will dominate the universe completely. What does that mean for the ultimate fate of the cosmos? Well, unless something changes, the universe will continue expanding forever, and the expansion will keep accelerating. Galaxies will drift apart faster and faster until they're moving away from each other faster than light. Eventually, we won't be able to see distant galaxies at all. The observable universe will shrink, isolated bubble by isolated bubble. Stars will eventually exhaust their fuel and burn out. Black holes will evaporate through Hawking radiation over timescales so vast they make the current age of the universe look like a blink. And ultimately, the universe will approach a state called heat death. Maximum entropy, uniform temperature, no energy available to do work, no structure, no life, no information. Just an endless, dark, cold void expanding forever. But that's trillions of years away. For now, we live in a special era. A cosmic golden age when the universe is mature enough to have interesting structure. Stars are still being born, and life has emerged to contemplate its own origins. Let's zoom back to that initial question one more time. Did the universe really come from nothing? The honest answer is we don't know. Not yet. We have compelling theories that explain how the universe evolved from a fraction of a second after the Big Bang to the present day. We can trace cosmic history with remarkable precision. But that initial moment, time zero, remains veiled in mystery. Some of the most promising current research involves quantum gravity, an attempt to merge quantum mechanics with general relativity. These two theories are the pillars of modern physics, but they contradict each other at extreme scales. General relativity describes gravity as the curvature of spacetime, and it works beautifully for large objects: planets, stars, galaxies, the universe itself. Quantum mechanics describes the behavior of tiny particles, and it's incredibly accurate for atoms and subatomic particles. But when you try to apply both theories simultaneously, like at the Big Bang where you have the entire universe compressed to quantum scales, the math breaks down. Equations spit out infinities. Predictions become meaningless. Physicists have been working for decades to find a theory of quantum gravity that could resolve this. String theory is one candidate, proposing that fundamental particles aren't point-like but tiny vibrating strings of energy. Loop quantum gravity is another, suggesting that spacetime itself is granular at the smallest scales, made of tiny loops woven together into a fabric. Both approaches offer tantalizing hints about what might have happened at the Big Bang, but neither has been experimentally confirmed. What would a complete theory of quantum gravity tell us? It might reveal that the Big Bang singularity, that point of infinite density where our equations currently fail, isn't actually singular at all. It might show that the universe bounced from a previous contracting phase, part of an eternal cycle of expansion and contraction. Or it might confirm that time truly begins at the Big Bang with nothing, not even physics, existing before it. One of the most exciting recent developments comes from the intersection of quantum information theory and cosmology. Some physicists now think that information might be more fundamental than matter or energy. In this view, the universe is essentially a vast quantum computer, processing information according to the laws of physics. The Big Bang would then be the moment when the universe booted up, initializing with a specific set of quantum information that determined everything that followed. This connects to holographic principle, one of the strangest ideas in theoretical physics. It suggests that all the information contained in a volume of space can be encoded on the boundary of that space, like a hologram. Applied to the entire universe, this means that our three-dimensional reality might be a projection from information encoded on a distant two-dimensional surface. If true, it would fundamentally change how we think about space, time, and existence itself. But even with all these sophisticated theories, we bump up against deep philosophical questions. Why do these laws exist? Why is there something rather than nothing? Why does the universe seem to operate according to mathematical principles that human minds can comprehend? The physicist Eugene Wigner once wrote about the unreasonable effectiveness of mathematics in the natural sciences. Why should abstract mathematical concepts invented by humans perfectly describe the behavior of the cosmos? Pythagoras discovered his theorem about right triangles over 2,500 years ago, and it still works not just on Earth but anywhere in the universe. Einstein's equations of general relativity, written down with pencil and paper in 1915, predicted the existence of black holes, gravitational waves, and the expansion of the universe, all of which we've now confirmed. Mathematics invented before we knew these things existed somehow describes them perfectly. Is mathematics something we discover or something we invent? Is it built into the fabric of reality? Or is it just a useful tool our brains created? These might sound like philosophical questions, but they're deeply connected to understanding the origin of the universe. If mathematics is fundamental to reality, then maybe the universe exists because certain mathematical structures must exist, and a universe is simply the physical manifestation of those structures. The philosopher and cosmologist Max Tegmark takes this idea to its logical extreme with his mathematical universe hypothesis. He proposes that physical reality is mathematics. Not that it's described by mathematics, but that it literally is a mathematical structure. In this view, our universe is just one of many mathematical structures that exist in a realm of pure abstraction. Conscious beings like us exist within certain mathematical structures that are complex enough to support life and consciousness. It's a dizzying idea, and most physicists remain skeptical. But it speaks to just how fundamental these questions become when you trace them to their origin. Here's something else to consider: the horizon problem. The cosmic microwave background has almost exactly the same temperature in every direction, to within 1 part in 100,000. How is that possible? Different regions of the sky that we observe are so far apart that light hasn't had enough time to travel between them even in the entire age of the universe. They've never been in contact. So how did they end up at the same temperature? This was one of the puzzles that led to inflation theory. If the universe underwent that brief period of faster-than-light expansion, then regions that seem unconnected now were actually close together before inflation. They had time to reach the same temperature, and then inflation rapidly separated them. It solves the problem elegantly, which is why inflation has become a cornerstone of modern cosmology. But inflation creates its own puzzles. What caused inflation to start? What caused it to stop? And perhaps most intriguingly, if inflation happened, it probably never completely stops everywhere at once. In some regions of space, inflation might still be happening right now, creating new bubble universes constantly. This is called eternal inflation, and it naturally leads to that multiverse scenario I mentioned earlier. If eternal inflation is correct, then the Big Bang that created our universe wasn't the only one. There was no first Big Bang. Bubble universes are constantly budding off from inflating space, each with potentially different physics. Most of these universes would be lifeless, with properties that don't allow stars or atoms. But given infinite time and infinite space, some bubbles would have conditions suitable for life. We exist in one of those. This actually makes the question of how something came from nothing even more interesting. Maybe something didn't come from nothing just once. Maybe it's happening all the time, eternally, with our universe being just one tiny bubble in an infinite, ever-growing foam of realities. Of course, there's a problem with multiverse theories. They might not be testable. If other universes are forever beyond our ability to observe, even in principle, is the multiverse idea really science? Or is it just metaphysics dressed up in equations? Some physicists argue that we might find indirect evidence. If our universe bubble collided with another universe bubble in the distant past, it might have left a mark on the cosmic microwave background, a circular pattern different from the rest of the sky. Researchers have looked for these collision signatures. So far, they haven't found any convincing evidence, but the search continues. Another line of evidence could come from the fine-tuning problem I mentioned before. If we eventually develop a theory that predicts the values of fundamental constants, and those predictions match observations without requiring a multiverse, then Occam's razor would favor the simpler explanation. But if the theory gives us no reason why constants have the values they do, the multiverse becomes more attractive as an explanation. Let's talk about one more mind-bending concept: the possibility that the universe is cyclical. What if the Big Bang wasn't the beginning, but just a transition? Some models propose that the universe undergoes endless cycles of expansion and contraction. The universe expands, as ours is doing now, then eventually stops and begins to contract. All matter falls back together in a big crunch, which then bounces into a new Big Bang, starting the cycle over. The latest version of this idea, called ekpyrotic cosmology, borrows from string theory. It suggests that our three-dimensional universe is like a membrane, or brain, floating in a higher dimensional space. There might be other brains nearby. When two brains collide, the energy released creates what looks to us like a Big Bang. The universe expands, driven by dark energy, until eventually conditions are right for another collision, and the cycle repeats. In these cyclic models, there's no beginning. The universe is eternal, undergoing infinite cycles of death and rebirth. Our Big Bang was just the latest chapter in an endless story. Which of these scenarios is correct? Is the universe a quantum fluctuation, a mathematical structure, one bubble in an infinite multiverse, part of an eternal cycle, or something else we haven't thought of yet? The truth is, we don't know, but we're getting closer to finding out. Right now, multiple experiments are pushing the boundaries of cosmology. The James Webb Space Telescope is looking at the earliest galaxies, testing our theories about how structure formed. Gravitational wave detectors like LIGO are listening to the echoes of colliding black holes and neutron stars, giving us new ways to probe the universe. Particle accelerators like the Large Hadron Collider are recreating conditions similar to those just after the Big Bang, searching for new physics that might explain dark matter. Future experiments might detect primordial gravitational waves, ripples in spacetime created during inflation, which would be direct evidence that inflation actually occurred. Others are searching for dark matter particles, trying to figure out what that invisible 27% of the universe actually is. And theorists continue to work on quantum gravity, hoping to build a complete theory that describes the moment of creation itself. But even if we answer all these questions, even if we figure out exactly how the universe began and why, we'll still face that final, ultimate question. Why does anything exist at all? Maybe that question has an answer. Maybe existence is simply inevitable, a logical necessity that couldn't be otherwise. Or maybe the question itself is flawed, based on assumptions that don't apply to the universe as a whole. Or maybe, just maybe, we'll never know. Maybe some questions are forever beyond the reach of science, not because we're not smart enough, but because they exist outside the framework of cause and effect, logic and reason that science requires. But that doesn't mean we should stop asking, because the search for answers, the attempt to understand our cosmic origins, tells us something profound about what it means to be human. We're the universe's way of knowing itself. We're matter that has become conscious, stardust that can contemplate stars. Every atom in your body was forged in the heart of a dying star. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was created through nuclear fusion in stars that lived and died billions of years ago. You are literally made of star stuff, assembled into a pattern complex enough to ask where it came from. And here's the beautiful part. We're still part of that cosmic story. The universe is still evolving, still creating, still becoming. 13.8 billion years after the Big Bang, matter has organized itself into galaxies and stars and planets and life and consciousness. Who knows what will happen in the next 13.8 billion years? When you look up at the night sky, you're not just seeing space. You're seeing time. The light from the nearest star, Proxima Centauri, left that star over 4 years ago. The light from the Andromeda galaxy started its journey 2.5 million years ago, when our ancestors were just learning to use stone tools. And the cosmic microwave background radiation comes from 13.8 billion years ago, carrying information from when the universe was younger than a newborn baby. We live in an expanding bubble of light, bounded by the cosmic horizon beyond which we can never see. But within that bubble, we can observe the entire history of the cosmos, from the first atoms to the latest galaxies. We can trace the evolution of complexity from a featureless plasma to stars, to planets, to life, to minds that can comprehend the whole story. That story includes you. It includes everyone who has ever lived and everyone who ever will live. We're all children of the Big Bang, participants in the universe's grand adventure from simplicity to complexity, from uniformity to diversity, from nothing or something very much like it to everything. The question of how the universe began might not have a simple answer. It might not have a final answer, but pursuing that question has taught us more about reality than any other endeavor in human history. It's shown us that the universe is stranger, older, larger, and more magnificent than anyone imagined. It's revealed that we live in a cosmos governed by comprehensible laws, where matter and energy transform according to mathematical principles we can discover and understand. And perhaps most importantly, it's shown us that we're not separate from the universe. We're not observers standing outside, looking in. We're part of it. The universe made us, and now we're making sense of the universe. The cosmos is not only queerer than we suppose, as the biologist J.B.S. Haldane said, it's queerer than we can suppose. But that hasn't stopped us from trying to understand it, and we've made remarkable progress. From ancient myths about cosmic eggs and primordial waters, to medieval arguments about whether the universe had a beginning, to Einstein's equations revealing that space and time are dynamic and curved, to Hubble's discovery that the universe is expanding, to the detection of the cosmic microwave background, to inflation theory, to dark matter and dark energy, to quantum cosmology and the multiverse, the story of how we've come to understand our origins is as epic as the origin itself. We stand at an extraordinary moment in human history. For the first time, we can look back to nearly the beginning of time itself. We can test our theories against observation. We can make predictions and see if they come true. The universe is not an impenetrable mystery. It's a puzzle we're solving piece by piece, equation by equation, observation by observation. Will we ever know everything? Probably not. The universe is vast, and we are small. But we're not helpless. We're not ignorant. We have tools: mathematics, observation, reason, creativity. We have evidence: the light of distant stars, the whisper of ancient radiation, the elegant equations that describe how everything works. And we have something else, something uniquely human: the drive to ask why, to seek answers, to push the boundaries of knowledge further and further until we touch the very fabric of reality itself. So when you ask how the universe started from nothing, remember that the answer, whatever it turns out to be, is written in the stars above you, in the atoms that comprise you, and in the very space between. The universe has been telling us its origin story since the beginning. We're finally learning how to listen, and that story, that magnificent, strange, beautiful story of how everything came to be, is the greatest story ever told. Because it's not just the universe's story, it's our story too. We're the universe experiencing itself, asking itself questions, seeking its own origins. In a very real sense, when we study cosmology, the universe is studying itself. The Big Bang wasn't just the birth of space and time. It was the beginning of everything that would follow. Every star that would shine, every planet that would form, every life that would emerge, every thought that would be thought. All of it encoded in those first moments, in those quantum fluctuations that seeded galaxies, in that inflatant field that drove expansion, in those fundamental forces that shaped matter. From nothing or something indistinguishable from it came everything. From chaos came order. From simplicity came complexity. From uniformity came diversity. And from mere matter came life and consciousness and wonder. The universe didn't have to be comprehensible. It didn't have to follow mathematical laws. It didn't have to create conditions suitable for life. But it did. And now here we are, 13.8 billion years later, conscious beings made of stardust, asking how it all began. We might never have a complete answer. The very concept of nothing might be incoherent, an idea our minds created that doesn't correspond to anything real. Maybe there always was something in some form, and the Big Bang was just a transformation rather than a creation. Or maybe nothing is unstable. Maybe the quantum laws that govern reality make it impossible for true nothingness to persist. Maybe something must emerge from nothing, not because of any external cause, but because nothing itself contains the seeds of something. The quantum vacuum is never empty. It seethes with virtual particles, with potential energy, with possibility. Perhaps the universe is simply the ultimate expression of that possibility made real. Whatever the answer, we know this: the universe exists. We exist. And against all odds, we're figuring out how and why. That's no small achievement for a species that's only been doing science for a few hundred years, that's only known about the Big Bang for less than a century, that's only been able to see the cosmic microwave background for a few decades. Imagine what we might know in another century or another millennium. Imagine what questions we'll be asking then. Imagine what mysteries we'll have solved and what new mysteries we'll have discovered. The story of how the universe began is still being written, not just by physicists and cosmologists, but by everyone who looks up at the night sky and asks, how? Why? Where did all this come from? Those questions might never have final answers, but the asking matters. The searching matters, because in seeking to understand how the universe began, we're engaging in perhaps the most profoundly human activity there is, trying to know ourselves, our place, our origins in this vast cosmic arena. We are made of atoms forged in stars, evolved on a planet orbiting an ordinary star in an ordinary galaxy, contemplating our origins in a universe that somehow emerged from apparent nothingness 13.8 billion years ago. We are the universe made conscious, nature's way of knowing itself. And if that's not worthy of wonder, if that's not worth celebrating, if that's not motivation enough to keep asking questions and seeking answers, then I don't know what is. The universe started from nothing, or from something, or from a quantum fluctuation, or from mathematics, or from a previous universe, or from something we haven't thought of yet. We don't know for certain, not yet, but we're working on it. And that's what makes this such an exciting time to be alive. We're living in the era when humanity is finally beginning to understand its cosmic origins, when we can trace our lineage back not just to our parents or our evolutionary ancestors, but to the Big Bang itself. Every question we answer raises new questions. Every mystery we solve reveals deeper mysteries. And that's exactly how it should be. Because the quest to understand how the universe began isn't just about satisfying intellectual curiosity. It's about understanding reality at its most fundamental level. It's about knowing what we're made of, where we came from, and where we're going. The universe didn't have to be knowable. It didn't have to make sense. But it does. And we're the lucky few among all the matter in the cosmos who can think about it, study it, and gradually, piece by piece, understand it. So the next time someone asks you how the universe started from nothing, you can tell them, with a bang or a bounce or a fluctuation, with inflation and dark matter and cosmic microwave background radiation, with mathematics and quantum mechanics and theories we're still developing. And most importantly, with us asking that question, searching for that answer, marveling at the fact that we exist at all in this strange, beautiful, mysterious universe that somehow came from nothing and became everything. But let's dig deeper into something that challenges our intuition even more: the nature of time itself near the Big Bang. We experience time as flowing in one direction, from past to future. We remember yesterday but not tomorrow. Eggs break but don't spontaneously reassemble. This arrow of time seems fundamental to existence. Yet, at the quantum level, most physical laws work equally well forwards or backwards in time. So where does this arrow come from? The answer lies in entropy, a measure of disorder. The second law of thermodynamics tells us that entropy always increases in a closed system. Ice cubes melt in warm water. Hot coffee cools down. The universe naturally moves from order to disorder. This gives time its direction. But here's the puzzle. If entropy always increases, then the universe must have started in an extremely low entropy state. The Big Bang was a state of remarkable order, not chaos. All that energy and matter compressed into an infinitesimally small space was actually highly organized. Think about it. If you took all the matter in the universe today and tried to compress it into a single point, you'd create a black hole which has very high entropy. But the early universe wasn't a black hole. It was smooth, uniform, incredibly hot and dense, but distributed evenly. This uniformity represents low entropy because there are fewer ways to arrange matter when it's all spread out evenly compared to the countless configurations possible when matter clumps into stars, galaxies, and black holes. So the universe began in a special low-entropy state and has been increasing in entropy ever since. Stars form and die. Black holes grow. The cosmos becomes more disordered over time. But why did it start that way? This is sometimes called the past hypothesis, the assumption that the universe had low entropy at the beginning. We don't know why. It might be a consequence of whatever mechanism created the universe, or it might be a selection effect. If time's arrow emerges from increasing entropy, then conscious beings who experience time flowing forward would only exist in universes that started with low entropy. Now let's explore something that sounds like science fiction but is actually serious physics. Could we create a universe in a laboratory? Physicist Alan Guth, the father of inflation theory, once calculated that it might be possible to create a baby universe with just about 10 kilograms of matter compressed to incredibly high density. The idea is that if you could recreate the conditions of inflation in a tiny region, that region might inflate and pinch off from our universe, becoming its own separate spacetime. To observers in our universe, it might look like a black hole. But inside, it would be an entire inflating universe, potentially growing to cosmic proportions in its own reference frame. Before you start worrying about rogue physicists manufacturing universes in their basements, there are enormous technical challenges. We're talking about energy densities far beyond anything we can achieve with current technology. But the fact that it's even theoretically possible raises profound questions. If sufficiently advanced civilizations could create universes, does that mean our universe might have been created by someone else? Not in a religious sense, but in a literal scientific sense. Some physicists have speculated about cosmological natural selection, an idea proposed by Lee Smolin. The hypothesis suggests that universes that produce many black holes have a reproductive advantage because new universes might be born inside black holes. Over cosmic generations, this could lead to universes fine-tuned to produce black holes, which coincidentally might also be universes capable of supporting complex chemistry and life. It's a speculative idea, lacking direct evidence, but it shows how creative scientists get when trying to explain why our universe has the properties it does. Let's shift gears and talk about the shape of the universe. When people hear that the universe is expanding, they often imagine it like a balloon inflating, with galaxies as dots on the surface moving apart. But that's only an analogy. The universe doesn't expand into anything. Space itself is what's expanding. But this raises a question. Does space go on forever, or does it curve back on itself? There are three possibilities for the geometry of the universe. It could be flat, like an infinite sheet of paper, extending forever in all directions. It could be positively curved, like the surface of a sphere, meaning if you traveled far enough in one direction, you'd eventually return to where you started. Or it could be negatively curved, like a saddle, also infinite but with a different geometry. Measurements of the cosmic microwave background tell us that the universe is remarkably flat. Not perfectly flat, but flat to within 1% as far as we can measure. If the universe were a sphere, its radius would be at least hundreds of times larger than the observable universe. For all practical purposes, space in our cosmic neighborhood appears flat. But here's where it gets interesting. Even if space is geometrically flat on large scales, it could still have a topology, a global shape that's different from simple infinite flatness. Imagine a video game where when you go off the right edge of the screen, you reappear on the left. The local geometry is flat, you're moving on a flat surface, but the global topology is connected in a loop. The universe could work similarly. It might be flat locally but wrapped around itself in complex ways on cosmic scales. Some researchers have searched for evidence of this by looking for repeating patterns in the cosmic microwave background. If the universe wrapped around itself, we might see the same structures appearing in different parts of the sky, like seeing your reflection in a hall of mirrors. So far, no convincing evidence has been found, suggesting that if the universe does have interesting topology, it's much larger than the observable universe. Speaking of the observable universe, let's clarify what that means. The observable universe is the region from which light has had time to reach us since the Big Bang. Its radius is about 46.5 billion light-years, even though the universe is only 13.8 billion years old. How is that possible? Because space has been expanding while light travels through it. A galaxy whose light took 13 billion years to reach us isn't 13 billion light-years away anymore. It's now about 30 billion light-years away because space has been stretching the whole time. But the total universe, the whole of space, could be vastly larger than what we can observe. It might even be infinite. If inflation is correct, the observable universe is an infinitesimally tiny patch of a much larger cosmos. Imagine Earth's surface as a metaphor. The observable universe would be like a tiny spot on the surface, maybe the size of a grain of sand compared to the entire planet. What lies beyond our cosmic horizon? Other galaxies, presumably similar to ours. Other structures, other stars, possibly other life. But we can never observe them because their light will never reach us. As the universe continues to expand and accelerate, the cosmic horizon is actually shrinking. Distant galaxies are crossing the horizon right now, disappearing from view forever. In the far future, if the acceleration continues, civilizations will only be able to see their local group of galaxies. Everything else will have vanished beyond the horizon, leaving them in an island universe, isolated in an ocean of expanding space. Those future beings might not even be able to figure out that the Big Bang happened. The evidence, the distant galaxies, the cosmic microwave background might all be redshifted beyond detection. They'd live in a static-looking universe with no obvious signs of expansion or cosmic history. It makes you wonder what evidence we might be missing right now, what aspects of cosmic history might have already slipped beyond our ability to observe. Now let's tackle one of the most controversial topics in cosmology, the Boltzmann brain problem. It's a thought experiment that arises from taking seriously the implications of entropy and probability in an eternal universe. Here's the setup. If the universe exists forever and has a finite maximum entropy, then over infinite time, random thermal fluctuations will occasionally decrease entropy in local regions. Most of these fluctuations will be small, just a few particles arranged in unlikely ways. But very, very rarely larger fluctuations will occur. And if you wait long enough, infinite time, you'll get fluctuations large enough to form any structure, no matter how complex. This includes brains. A random thermal fluctuation could, in principle, assemble a functioning brain complete with memories, thoughts, and the experience of existing in a larger world. This brain, called a Boltzmann brain, would exist for a brief moment before dissipating back into chaos. But during its existence, it would be indistinguishable from your brain right now. It would have false memories of a past that never happened, existing in a universe that isn't really there. Here's the problem. If the universe is eternal and these random fluctuations happen, then for every real brain that evolved through natural processes over billions of years, there will be vastly more Boltzmann brains that popped into existence fully formed. The probability of you being a real brain with a real history is infinitesimally small compared to the probability of you being a Boltzmann brain with false memories. This sounds absurd, but it's a serious challenge for certain cosmological models. If your theory predicts that most observers should be Boltzmann brains, but you're confident you're not one, then something is wrong with the theory. This constraint has led physicists to reject some otherwise viable models of the universe's future. They call it selecting for theories with a Boltzmann brain problem that's manageable. The solution might be that the universe isn't eternal in a simple way. Maybe dark energy will change over time. Maybe the Big Rip will tear space apart. Maybe quantum effects will become important in ways we don't understand. Or maybe the multiverse framework provides an answer, with most observers existing in universes that don't last long enough for Boltzmann brains to dominate. Let's move to something more concrete. The cosmic web, the large-scale structure of the universe. On small scales, matter clumps into stars and galaxies. But zoom out far enough and you see an even grander pattern. Galaxies aren't randomly scattered through space. They're organized into filaments, sheets, and clusters, separated by vast voids where almost nothing exists. This structure emerged from those tiny fluctuations in the cosmic microwave background. Regions that were slightly denser had slightly more gravity. Over millions of years, gravity amplified these differences. Matter flowed along gravitational gradients, draining from the voids and accumulating in filaments. The result looks remarkably like a neural network, with galaxies connected by threads of dark matter and gas. The largest structure we found is the Hercules Corona Borealis Great Wall, a concentration of galaxy clusters spanning about 10 billion light-years. That's over 10% of the diameter of the observable universe. Structures this large challenge our understanding of how quickly things can assemble. The universe might not have been old enough for something so massive to form through gravity alone, suggesting we might be missing something about how structure develops. These enormous structures also tell us about the nature of dark matter. Computer simulations show that you need dark matter to form the cosmic web we observe. Without it, normal matter would be too diffuse, too hot, too affected by radiation pressure to clump together quickly enough. Dark matter acts as scaffolding, creating gravitational wells that normal matter falls into. Galaxies form where dark matter has already accumulated. But dark matter remains invisible. We've built detectors deep underground, shielded from cosmic rays, waiting for a dark matter particle to collide with normal matter. We've searched for evidence of dark matter particles annihilating each other and producing gamma rays. We've looked for tiny distortions in starlight caused by dark matter clumps. Despite decades of effort and increasingly sensitive experiments, we haven't directly detected a dark matter particle. This has led some physicists to wonder if dark matter is actually particles at all. Maybe it's something else entirely. One alternative is modified gravity, the idea that Einstein's equations need adjustment on cosmic scales. Instead of invisible matter creating extra gravity, maybe gravity itself behaves differently than we think over large distances. These modified gravity theories can explain some observations, but they struggle to explain everything that dark matter explains naturally, particularly the detailed structure we see in the cosmic microwave background and galaxy clusters. The smart money is still on dark matter being some type of particle we haven't discovered yet. The universe has surprised us before with unexpected particles. Neutrinos were predicted theoretically before they were detected. The Higgs boson was hypothesized for decades before the Large Hadron Collider found it. Dark matter might just be the next particle waiting to be discovered. What could dark matter be? The leading candidates are WIMPs, weakly interacting massive particles, which would be heavy particles that barely interact with normal matter. Another possibility is axions, incredibly light particles predicted by some extensions of the standard model of particle physics. Or it could be primordial black holes, formed in the early universe, too small and dark to be easily observed but collectively making up the missing mass. Each hypothesis makes different predictions about how dark matter should behave and how we might detect it. The next generation of experiments will be sensitive enough to test many of these ideas. Within the next couple of decades, we might finally know what dark matter is, solving one of the greatest mysteries in physics. But let's return to the moment of the Big Bang itself and explore a fascinating alternative to the standard picture: loop quantum cosmology. This approach applies loop quantum gravity, one candidate for a theory of quantum gravity, to the early universe. In this framework, space-time isn't infinitely divisible. At the Planck scale, about 10 to the minus 35 meters, space becomes granular, made of discrete loops of space-time. When you apply this to the Big Bang, something remarkable happens. The singularity, that point of infinite density where Einstein's equations break down, disappears. Instead, the Big Bang becomes a big bounce. As you trace cosmic history backward, the universe contracts, but it never reaches infinite density. When it gets down to Planck scale densities, quantum effects create a repulsive force that halts the collapse and reverses it, causing the universe to bounce back into expansion. If this is correct, our Big Bang was the rebound from a previous contracting phase. Before our universe expanded, there was another universe that contracted. This elegantly solves the problem of what came before the Big Bang. Another universe did, though not necessarily the same one with the same properties. Loop quantum cosmology makes testable predictions. It affects how perturbations evolve in the very early universe, which could leave signatures in the cosmic microwave background different from standard inflation. Astronomers are looking for these signatures now. If found, they would be evidence not just for quantum gravity but for a universe that existed before our Big Bang. Another approach to understanding the beginning involves conformal cyclic cosmology, an idea championed by Nobel laureate Roger Penrose. His proposal is mathematically sophisticated but conceptually audacious. He suggests that the infinite future of our universe, when everything has decayed and spread out, is mathematically equivalent to the infinitely dense Big Bang of a new universe. The end of one cosmic era becomes the beginning of the next. In this model, the universe goes through endless cycles or eons. Each aeon begins with a Big Bang and ends in a cold, empty state of maximum expansion. But in that final state, with no matter left to provide a sense of scale, the geometry of spacetime can be mathematically transformed into the initial conditions for a new Big Bang. Time doesn't end. It transitions into a new aeon. Penrose has claimed to find evidence for this in the cosmic microwave background. Circular patterns that could be the signatures of colliding black holes from a previous aeon. The evidence is controversial, with most cosmologists remaining skeptical, but it represents a radical reimagining of cosmic history. What these alternative models share is an attempt to eliminate the singularity, to show that the Big Bang wasn't truly a beginning but a transition. They suggest that something existed before, whether it was a previous universe, a quantum fluctuation in some larger structure, or a different phase of spacetime altogether. But even if these models are correct, they don't answer the ultimate question. They just push it back. If our universe bounced from a previous one, where did that one come from? If universes cycle eternally, why do they cycle? What sustains the cycle? What are the rules that govern transitions between cosmic eras? We might be approaching the limits of what physics can answer. Science requires causes and effects, events connected by physical laws. But when you ask about the origin of everything, including physical laws themselves, you're asking about something that might be outside the framework of cause and effect. It's like asking what's north of the North Pole. The question presupposes a framework, a direction called north, that doesn't apply at the pole itself. Some physicists, like Stephen Hawking in his later work, suggested that the question of absolute beginning might be resolved by quantum mechanics. In quantum theory, things don't need definite causes. Particles can appear and disappear spontaneously. Properties can be indefinite until measured. Hawking proposed that the universe has no boundary in time, that as you go back, time becomes space-like, and the very concept of a beginning dissolves into quantum uncertainty. In his view, asking what caused the Big Bang is like asking for the edge of a sphere. A sphere has no edge. Every point on its surface is like every other. Similarly, the universe might have no temporal edge, no first moment. Time would be finite in extent when you look backward, but there would be no boundary, no moment where time began. The universe would simply be a self-contained spacetime, existing without external cause or creation. This is philosophically profound but practically unsatisfying. It tells us that the universe exists as a complete space-time structure, but it doesn't explain why that structure exists or why it has the properties it does. Why is there a universe described by Einstein's equations rather than some other laws? Why does it have 3 dimensions of space and 1 of time rather than some other configuration? Why do particles have the masses they do? Why is the cosmological constant, the dark energy that drives acceleration, the value it is rather than 0 or something enormously larger? These questions about the fundamental parameters of physics are at the heart of what's called the fine-tuning problem. Many of the constants of nature appear finely tuned for life. If the strong nuclear force were slightly weaker, atomic nuclei wouldn't hold together. If it were slightly stronger, all hydrogen would have fused to helium in the early universe, leaving no fuel for stars. If electromagnetism were stronger, chemical bonds wouldn't form properly. If gravity were stronger, stars would burn out too quickly for life to evolve. The range of values that allows for a universe with stable atoms, long-lived stars, and complex chemistry is remarkably narrow. Some physicists estimate that changing certain constants by even 1% would make life impossible. Is this just coincidence, design, or is there a deeper explanation? The multiverse provides one answer. If countless universes exist with different constants, we necessarily find ourselves in one of the rare universes where the constants allow life to exist. It's a selection effect. We're not special. We're just lucky. Or rather, we're inevitable given enough universes. Somewhere in the vast multiverse, there would be universes with the right conditions, and observers would only exist in those universes to wonder about the fine-tuning. Critics argue that the multiverse explanation is unfalsifiable and therefore unscientific. If other universes are unobservable in principle, how can we test whether they exist? It's a fair criticism, but defenders point out that the multiverse might be a consequence of theories we can test. If inflation is correct and we find evidence for it, and inflation naturally produces multiple bubble universes, then the multiverse comes as part of the package. Others search for a theory that predicts the constants rather than just accepting them as arbitrary parameters. String theory, for instance, hopes to derive all the constants of nature from a single underlying principle. If successful, it would show that the constants couldn't be any other way, that they're determined by mathematical necessity. The universe would be fine-tuned not by chance or design, but by logical inevitability. We don't have that theory yet. String theory has been promising for decades, but hasn't made the definitive predictions needed to confirm or refute it. The mathematics is beautiful and sophisticated, but without experimental verification, it remains speculative. Meanwhile, physicists continue exploring the parameter space of possible universes. They run computer simulations with different values for the constants, seeing what kinds of cosmos result. Some combinations produce universes that collapse immediately. Others expand too fast for anything to form. Some have chemistry but no stable atoms. Others have atoms but no way to form complex structures. The diversity is astounding. Change the constants just a bit, and you get a radically different universe. Ours seems to sit in a sweet spot, where multiple independent constants happen to have values that together allow for stars, planets, and life. Is that sweet spot large or small? Are there many ways to make a life-supporting universe, or just one narrow path? We're beginning to map out the answer one simulation at a time. Here's something that will truly bend your mind: the holographic principle and what it suggests about the fundamental nature of reality. In the 1990s, physicists studying black holes stumbled onto something remarkable. They found that all the information contained within a black hole can be described by data encoded on its surface, the event horizon. It's as if a three-dimensional object is completely described by a two-dimensional boundary, like a hologram. Then came the leap. If this is true for black holes, maybe it's true for the entire universe. Perhaps all of space-time, everything we experience as three-dimensional reality, is actually encoded on a distant two-dimensional surface. We would be living in a hologram, a projection from information stored on the boundary of the cosmos. This isn't just philosophical speculation. The mathematics works. The ADA-CFT correspondence, discovered by Juan Meldacena, provides a concrete example where a theory of gravity in one space can be exactly equivalent to a theory without gravity in a space with one fewer dimension. What does this mean for the origin of the universe? If reality is fundamentally information encoded on a boundary, then the Big Bang becomes the initialization of that information. The universe didn't explode into space. Information on the boundary began processing, and what we experience as the expanding universe is the unfolding of that computational process. This connects to another radical idea: digital physics, the notion that the universe is, at its deepest level, computational. Not that it can be simulated by a computer, but that it is a computation. Every particle, every field, every interaction is the universe computing its own evolution according to the laws of physics. If this is true, then asking what came before the Big Bang is like asking what comes before you turn on a computer. Nothing comes before. The computation begins, and time is simply the sequence of computational steps. The universe doesn't exist in time. Time is what we call the progression of the universe's computational state. Physicist Seth Lloyd has calculated that the universe has performed about 10 to the 120th operations since the Big Bang on about 10 to the 90th bits of information. That's a lot of computation, but it's finite. Every event in cosmic history, every thought you've ever had, every star that's ever formed, is part of this vast computational process. But who or what is running this computation? The universe itself. It's self-computing. The laws of physics are the algorithm, and matter and energy are the data. There's no external computer needed. The universe computes itself into existence, moment by moment, according to rules that are intrinsic to its structure. Now let's explore the concept of vacuum energy more deeply, because it's central to understanding both the Big Bang and the fate of the universe. In quantum field theory, empty space isn't empty. It's filled with fields, and those fields have energy even in their lowest state. This vacuum energy is real. We've measured it through the Casimir effect, where two uncharged metal plates in a vacuum attract each other because they restrict the quantum fluctuations between them. But here's the problem. When physicists calculate how much vacuum energy there should be based on quantum field theory, they get a number that's 10 to the 120th power larger than what we observe. That's not a typo. The theoretical prediction is off by 120 orders of magnitude. This is the cosmological constant problem, and it's one of the most embarrassing failures in theoretical physics. Why does this matter for the universe's origin? Because vacuum energy is what drives cosmic acceleration. It's dark energy. And during inflation, vacuum energy was what powered the exponential expansion. If we could understand why the vacuum energy has the value it does, we might understand what triggered inflation and therefore what triggered the Big Bang. Some physicists think vacuum energy might change over time. What we call dark energy might not be constant. There's some evidence from distant supernovae that dark energy might have been slightly different billions of years ago, though the data is still uncertain. If dark energy evolves, it could mean that the vacuum has multiple stable states, and the universe can transition between them. This leads to the idea of vacuum decay. Imagine the universe is like a ball sitting in a valley between two mountains. It's stable, but there's a deeper valley on the other side of one mountain. Through quantum tunneling, the ball could spontaneously jump through the mountain to the lower valley. If our vacuum isn't in the absolute lowest energy state, it could decay to a lower state. When that happens, a bubble of new vacuum would form somewhere in space and expand at the speed of light, converting everything it touches to the new vacuum. This would be catastrophic. The properties of particles would change instantly. Atoms would no longer be stable. Chemistry would stop working. Everything would be destroyed and replaced by matter with different properties. The good news is that if our vacuum is metastable, the timescale for decay could be vastly longer than the current age of the universe. We're probably safe. Probably. But it raises an interesting possibility for the Big Bang. Maybe our universe was born from a vacuum decay event in a pre-existing space. A bubble of new vacuum expanded rapidly, and that expansion is what we call the Big Bang. We would be living inside the bubble, unaware of whatever exists outside. Let's shift to discuss antimatter, because it presents one of the deepest mysteries about the universe's beginning. According to the standard model of particle physics, the Big Bang should have created equal amounts of matter and antimatter. When matter and antimatter meet, they annihilate, converting back into pure energy. So why is there anything at all? Why didn't all the matter and antimatter annihilate, leaving only radiation? Somehow there was a tiny asymmetry. For every billion antimatter particles, there were 1,000,000,001 matter particles. After all the annihilation, that one extra matter particle in every billion survived. That tiny excess is everything we see today. Every star, every planet, every atom in your body. You are the residue of an ancient annihilation. But why was there an asymmetry? We don't fully know. The physics of matter and antimatter is almost perfectly symmetric, but not quite. There are subtle differences in how certain particles decay, a phenomenon called CP violation. These differences are too small to account for all the observed asymmetry, so there must be additional physics we haven't discovered yet. Some theories propose that the asymmetry was generated during the hot, dense conditions right after the Big Bang. Heavy particles that no longer exist in the universe today decayed in ways that slightly favored matter over antimatter. Others suggest that the asymmetry came from inflation itself, with quantum fluctuations during inflation creating slightly more matter than antimatter. This is one of the big questions that particle accelerators like the Large Hadron Collider are trying to answer. By recreating the conditions of the early universe, physicists hope to discover new particles and new interactions that explain why matter won. Here's another puzzle: magnetic monopoles. In the 1930s, physicist Paul Dirac showed that if magnetic monopoles exist, isolated north or south magnetic poles, it would explain why electric charge is quantized, why it comes in discrete units. It's an elegant idea, and many theories of particle physics predict that monopoles should have been created in enormous numbers during the Big Bang. But we've never found one. Not a single magnetic monopole has ever been detected. Where are they? Inflation provides an answer. If the universe underwent exponential expansion, any monopoles created before inflation would be diluted to incredibly low densities. There might be only one monopole in the entire observable universe, making detection essentially impossible. The absence of monopoles is actually evidence for inflation. Let's talk about the role of symmetry in shaping the universe. In physics, symmetry means that something looks the same after a transformation. A sphere looks the same if you rotate it. The laws of physics look the same if you shift time forward or backward. Symmetries are deeply connected to conservation laws through Noether's theorem. Time symmetry gives you conservation of energy, space symmetry gives conservation of momentum, and so on. In the early universe, physicists believe there was a grand unified symmetry, where all the forces of nature except gravity were unified into a single force. As the universe cooled, this symmetry broke. The forces separated into the strong nuclear force, the weak nuclear force, and electromagnetism. This is called spontaneous symmetry breaking, and it's like water freezing into ice. Water is symmetric, looking the same in all directions. But when it freezes, ice crystals form with specific orientations, breaking the symmetry. Each symmetry-breaking event released energy and created distinct particles associated with each force. The universe went through multiple phase transitions, each one reshaping the cosmos. The separation of forces determined which particles could exist and how they interacted. The universe we live in is the result of this cascade of broken symmetries. But why did symmetries break the way they did? Why this pattern of forces and particles rather than some other configuration? These might be accidents, random outcomes of quantum fluctuations during the cooling of the early universe. Or they might be determined by deeper principles we haven't discovered. Now consider the role of neutrinos in the early universe. These ghostly particles barely interact with matter. Trillions pass through your body every second from the sun, and you never feel them. But in the first second after the Big Bang, neutrinos played a crucial role. They were in thermal equilibrium with the hot plasma, constantly interacting with protons, neutrons, and electrons. When the universe was about 1 second old, it cooled enough that neutrinos stopped interacting with other particles. They decoupled, forming a cosmic neutrino background analogous to the cosmic microwave background, but even more ancient. These relic neutrinos are still out there, filling space, though they're too low energy to detect with current technology. Future experiments might detect the cosmic neutrino background, giving us a snapshot of the universe at 1 second old. That would be extraordinary. The cosmic microwave background shows us the universe at 380,000 years. The cosmic neutrino background would let us peer much closer to the beginning. Neutrinos also influenced structure formation. They move at nearly the speed of light, so in the early universe, they streamed freely across space, smoothing out small-scale structures. This affected how galaxies formed. By measuring the distribution of galaxies today, cosmologists can infer properties of neutrinos, including their mass. It's a beautiful example of how cosmology and particle physics inform each other. Let's explore the concept of eternal inflation in more depth. Standard inflation says the universe underwent a brief period of exponential expansion and then stopped. But in many models, inflation doesn't stop everywhere at once. Some regions exit inflation while others continue inflating. Those inflating regions grow exponentially, spawning new regions that might exit or continue inflating themselves. The result is a fractal structure of bubble universes constantly being created within an eternally inflating background. Our universe is one bubble where inflation ended. But out beyond our cosmic horizon, inflation continues, creating new bubbles endlessly. This process has no beginning and no end. Once inflation starts, it never completely stops. If eternal inflation is correct, asking when the Big Bang happened becomes complicated. Our Big Bang happened 13.8 billion years ago, but other bubble universes had their Big Bangs at different times. Some bubbles are older than ours, some younger, and the inflating space between bubbles has been inflating eternally, with no definite starting point. Some physicists find this disturbing. Eternal inflation predicts that everything that can happen will happen somewhere in the infinite multiverse. Every possible history, every quantum outcome, realizes in some bubble universe. There are bubbles where dinosaurs never went extinct, where humans never evolved, where the laws of physics are different. There are even bubbles where someone exactly like you makes every possible decision at every moment of life. This raises the measure problem. If there are infinitely many of everything, how do you calculate probabilities? What does it mean to say something is likely or unlikely when it happens infinitely many times? Physicists have struggled with this, trying to define a meaningful way to count outcomes in an infinite multiverse. Various proposals exist, but none is fully satisfactory. Despite these conceptual challenges, eternal inflation makes some testable predictions. It predicts how quantum fluctuations during inflation should look, which affects the patterns we see in the cosmic microwave background. Future observations might confirm or rule out specific models of eternal inflation. Now let's discuss something more speculative: the possibility that the universe is a simulation. This idea, popularized by philosopher Nick Bostrom, suggests that if civilizations can eventually create detailed simulations of universes, and if they choose to run many such simulations, then statistically most conscious observers would be in simulations rather than base reality. What does this mean for the Big Bang? If we're in a simulation, the Big Bang would be the initialization of the simulation, the starting conditions programmed by whoever is running it. The laws of physics would be the rules of the simulation. The fine-tuning of constants would make sense because they were chosen deliberately to create an interesting universe. Most physicists don't take this idea too seriously, not because it's impossible, but because it's unfalsifiable and doesn't help us make predictions. Whether we're in a simulation or not, we still experience the same physics, and we still need to understand how that physics works. The simulation hypothesis doesn't provide shortcuts to understanding, but it does raise an interesting point about the nature of explanation. Even if we discover a theory of everything that explains all the constants and all the laws of physics, we can still ask why that theory is true rather than some other theory. We might face an infinite regress of explanations. The simulation hypothesis is just one way of cutting off that regress. The ultimate explanation is that someone chose these rules, but that just pushes the question back. Who chose and why did they exist? Perhaps there is no ultimate explanation. Perhaps existence is a brute fact, something that simply is without further reason. Or perhaps there's a logical necessity to existence, some argument we haven't found yet that shows why there must be something rather than nothing. The philosopher Gottfried Leibniz asked the primordial question, why is there something rather than nothing? It's been centuries, and we still don't have a definitive answer. Physics can tell us how the universe evolved from early conditions. It can even tell us how those conditions might have arisen from quantum fluctuations or vacuum instabilities. But it can't tell us why quantum mechanics exists, why there's a quantum vacuum that can fluctuate, why there are laws of physics at all. Maybe that's where physics ends and philosophy begins. Or maybe it's where our current physics ends and a deeper physics awaits discovery. The history of science is full of questions that seemed philosophical or even religious until we found scientific answers. The origin of life, the nature of consciousness, the structure of matter, all of these were once beyond science's reach. Now we're making progress on all of them. Perhaps the origin of everything will be the same. What seems like an unanswerable metaphysical question might have a physical answer we just haven't thought of yet. Let's consider one more radical idea: cosmological natural selection and variation with a computational twist. What if universes aren't just created randomly but undergo something like evolution? Physicist Lee Smolin proposed that baby universes might be born inside black holes, inheriting properties from their parent universe with slight variations. Over cosmic generations, this would lead to selection for universes that produce many black holes. But we can extend this idea. If the universe is computational, as some theories suggest, then each baby universe would inherit computational rules from its parent, the laws of physics with slight mutations. Most mutations would produce unstable or boring universes. But occasionally, a mutation would produce a universe even better at making more universes. Over time, the multiverse would fill with universes descended from the most prolific parents. Could this explain fine-tuning? Maybe universes with properties like ours are particularly good at reproduction. The conditions that allow complex chemistry, long-lived stars, and potentially life might also be conditions that produce many black holes or other mechanisms for creating baby universes. We would exist in this kind of universe not by coincidence or design, but by selection. This idea is highly speculative and faces serious challenges. We don't know if baby universes are born in black holes. We don't know if physical laws can vary between parent and child universes. We don't know if there's a meaningful sense in which one set of laws is more fit than another. But it's an example of how physicists are trying to think beyond the traditional frameworks to explain why the universe is the way it is. Here's something more concrete: primordial gravitational waves. During inflation, quantum fluctuations didn't just affect the density of matter. They also created ripples in the fabric of space-time itself, gravitational waves. These primordial gravitational waves would have left a specific signature in the cosmic microwave background, a pattern of polarization called B-modes. Detecting B-modes would be direct evidence for inflation. Several experiments are searching for them now, using increasingly sensitive instruments stationed in Antarctica and other locations chosen for their clear, dry atmospheres. There was excitement in 2014 when the BICEP-2 experiment claimed detection, but further analysis showed the signal was contaminated by dust in our galaxy. The search continues. Finding primordial B-modes would be a landmark discovery, confirming that inflation happened and telling us about the energy scale of inflation. It would constrain models of how inflation occurred and what kind of field drove it. We'd finally have direct evidence for what happened in the first fraction of a second after time began. Gravitational waves from the Big Bang would also carry information about the pre-inflationary epoch if one existed. Some models predict that features in the pre-inflation state would leave imprints on gravitational waves. By studying these waves, we might learn about what came before inflation, probing even closer to the absolute beginning. Another window into the early universe comes from light element abundances. In the first few minutes after the Big Bang, the universe was a nuclear reactor, fusing protons and neutrons into helium, deuterium, and lithium. The ratios of these elements depend on conditions during nucleosynthesis, particularly the density of normal matter and the number of neutrino types. When we measure these ratios in ancient gas clouds and compare them to predictions from Big Bang nucleosynthesis, they match beautifully. This is some of the strongest evidence for the Big Bang. But there's a small puzzle called the lithium problem. We observe less lithium-7 than predicted. The discrepancy isn't huge, but it's persistent and unexplained. Possible solutions range from mundane to exotic. Maybe stars destroy lithium more efficiently than we thought. Maybe there were unexpected nuclear reactions in the early universe. Or maybe, just maybe, physics in the first few minutes wasn't quite what we think. Some physicists have proposed that particles beyond the standard model affected nucleosynthesis. If true, the lithium problem would be a clue to new physics operating at the dawn of time. Let's dive into the concept of causal structure and how it relates to the Big Bang. In relativity, events are connected by light cones. Everything that can influence you lies in your past light cone. Everything you can influence lies in your future light cone. Events outside these cones are causally disconnected from you. They can't affect you and you can't affect them. Now apply this to the entire universe. If you trace light cones backward from different regions of the cosmic microwave background, you find that many regions have never been in causal contact. Their past light cones don't overlap. Yet these causally disconnected regions have the same temperature, the same properties. How is that possible without some mechanism to coordinate them? This is another problem inflation solves elegantly. Before inflation, those regions were close together in causal contact. They reached equilibrium. Then inflation rapidly separated them, pushing them outside each other's light cones. The universe today shows the imprint of that earlier causal connection, even though those regions are now impossibly far apart. But this raises a profound question. What is the causal structure of the Big Bang itself? At the initial singularity, if it exists, all of spacetime is compressed to a point. Everything is in causal contact with everything else. Or is it? Does causality even make sense at the Big Bang? Can you have cause and effect when time itself is just beginning? Some physicists argue that causality breaks down at the Big Bang, that our usual notions of cause and effect don't apply. The Big Bang isn't caused by anything. It's simply the boundary of spacetime, the edge beyond which there is no before. Asking what caused it is like asking what's inside an atom's nucleus before protons and neutrons existed. The question assumes a structure that isn't there. Others suggest that quantum mechanics allows a kind of causality even at the Big Bang. In quantum cosmology, you can have probability amplitudes for different initial conditions. The universe begins in a superposition of all possible initial states, and what we observe is determined by which amplitude dominates. It's not deterministic causality, but it's not entirely random either. There's a mathematical structure determining which universes are more likely. Let's explore the Hartle-Hawking no-boundary proposal more deeply. James Hartle and Stephen Hawking proposed that the universe has no boundary in imaginary time. In this framework, you use a mathematical trick where time becomes like a spatial dimension, changing the signature of spacetime. When you do this, the Big Bang singularity smooths out. The universe becomes a closed surface with no edges, like a sphere. In ordinary time, the universe has a beginning, but in imaginary time, it doesn't. It's a complete, finite, self-contained structure. The beginning of the universe in real time corresponds to the south pole of a sphere. Just as asking what's south of the South Pole is meaningless, asking what came before the Big Bang is meaningless. Time emerges from geometry. This proposal is mathematically elegant and philosophically satisfying to many physicists. It eliminates the need for initial conditions. The universe is simply the state it is because that's the most probable configuration given the laws of quantum gravity. But it's controversial. The mathematics involves some assumptions about quantum gravity that might not be valid. And the use of imaginary time, while mathematically convenient, raises questions about what it means physically. An alternative approach is canonical quantum cosmology, which treats the universe as a quantum system described by a wave function. The Wheeler-DeWitt equation is the key equation here, describing how the quantum state of the universe evolves. But it's a strange equation because it doesn't include time explicitly. Time is built into the universe rather than existing independently. Solutions to the Wheeler-DeWitt equation give probability distributions for different configurations of the universe. The Big Bang corresponds to a particular boundary condition on this wave function. Different choices of boundary condition give different predictions for what the universe should look like. Finding the right boundary condition is one of the major challenges in quantum cosmology. Some versions of quantum cosmology predict that the universe created itself through a quantum tunneling event. Imagine a particle tunneling through a barrier it doesn't have enough energy to overcome classically. Similarly, the universe might have tunneled from nothing, from a state with no space and no time, into existence. The probability for this is incredibly small, but in quantum mechanics, incredibly small isn't zero. Given enough time, or given the strange logic of quantum mechanics where time doesn't exist yet, the improbable becomes inevitable. This is physicist Alex Vilenkin's proposal. The universe is a quantum fluctuation from nothing, not from a quantum vacuum with fields and energy, but from literally nothing. No space, no time, no laws of physics. The universe, including the laws of physics themselves, spontaneously appeared. It's the ultimate free lunch, as cosmologist Alan Guth likes to say. Critics point out that this still assumes quantum mechanics exists as a framework. Where did quantum mechanics come from? Is it a law that exists independently of the universe, a kind of Platonic form floating in a realm of pure mathematics? Or did quantum mechanics also emerge somehow from nothing? These questions might be unanswerable. We might have reached the boundary of scientific inquiry, the point where physics gives way to metaphysics. Or we might just need a more radical idea, something beyond current physics, to understand the true origin. Let's talk about cosmic strings, topological defects that might have formed in the early universe during phase transitions. When symmetries break, sometimes the break doesn't occur uniformly. Defects form, like cracks in ice when water freezes. In three-dimensional space, these defects can be one-dimensional threads called cosmic strings. Cosmic strings would be incredibly dense, with masses comparable to a galaxy compressed into a thread narrower than an atom. They would distort space-time around them, bending light and creating gravitational effects. If they formed during the Big Bang, they would stretch across the universe, perhaps forming a vast network of strings and loops. For a while, cosmic strings were considered a possible seed for galaxy formation. The gravitational effects around strings could attract matter, forming the first large structures. But observations of the cosmic microwave background don't show the signatures that cosmic strings would produce. Either cosmic strings don't exist, or they're much rarer than once thought. Still, the search continues. Gravitational wave detectors might find strings, which would oscillate and produce gravitational waves. Finding cosmic strings would tell us about the energy scale of symmetry breaking in the early universe and confirm predictions of grand unified theories. Related to cosmic strings are domain walls, two-dimensional defects, and magnetic monopoles, zero-dimensional defects. Each would form under different conditions and leave different signatures. The absence of easily detectable defects is actually a constraint on theories of the early universe. Any theory predicting large numbers of defects is in trouble unless inflation diluted them beyond detectability. Now let's consider the anthropic principle more carefully. The weak anthropic principle simply states that we observe the universe to have properties compatible with our existence because if it didn't, we wouldn't be here to observe it. This is uncontroversial, almost a tautology. The strong anthropic principle is more contentious. It suggests that the universe must have properties that allow consciousness to develop at some point in its history. This seems to give consciousness a privileged role in physics, which makes many scientists uncomfortable. It sounds teleological, as if the universe has a purpose. But there's a version that's scientifically interesting. Participatory anthropic principle, suggested by physicist John Wheeler. In quantum mechanics, observation affects reality. Before measurement, systems exist in superpositions. Measurement collapses the wave function, selecting one outcome. Wheeler speculated that observers play a role in bringing the universe into existence. The act of observation retroactively determines the state of the early universe. This is wild speculation, extending quantum mechanics far beyond where we've tested it. But it raises interesting questions about the relationship between consciousness and physical reality. Does observation require consciousness? Or is any physical interaction that records information sufficient? If the latter, then the universe has been observing itself since the beginning, and consciousness is just a particularly complex form of observation. Let's shift to the observable consequences of different Big Bang scenarios. Suppose the Big Bang was actually a collision between two brains in a higher dimensional space, as in ekpyrotic cosmology. This would produce a different spectrum of density fluctuations than inflation produces. The differences are subtle but potentially measurable in the cosmic microwave background. Similarly, if the universe bounced from a previous contracting phase, as in loop quantum cosmology, there might be residual effects. The bounce would produce gravitational waves with a characteristic spectrum. It might also leave features in the distribution of matter that we could detect. Each theory of the Big Bang makes predictions. The challenge is that many predictions involve phenomena at energy scales we can't reach with particle accelerators or observations so subtle they're at the edge of what our instruments can detect. But as technology improves, we get closer to testing these ideas. Consider the Planck satellite, which mapped the cosmic microwave background with unprecedented precision. It measured temperature fluctuations to millionths of a degree and polarization patterns across the sky. Every new data release constrains theories of the early universe. Some models have been ruled out. Others remain viable. With each observation, we narrow the possibilities. Future experiments will be even more powerful. The Simons Observatory, the CMB-S4 project, and space-based missions are being designed to detect even fainter signals. Ground-based gravitational wave detectors are being upgraded to reach lower frequencies. Radio telescopes are mapping the distribution of hydrogen gas in the early universe, probing the cosmic dark ages. Within the next few decades, we might detect primordial gravitational waves, providing direct evidence for inflation. We might find new particles that explain dark matter. We might observe the earliest galaxies and see how they formed. Each discovery will be a piece of the puzzle, helping us understand how the universe began. But some questions might remain forever beyond observation. If there are parts of the universe beyond our cosmic horizon, we can never see them. If there are other universes in a multiverse, we can never visit them. If the Big Bang truly erased all information about any prior state, we can never recover it. This is the frustrating reality of cosmology. We're studying the universe from the inside with limited observational access. It's like trying to understand Earth's geography when you're confined to a small island. You can theorize about other continents, but you can't see them. You can infer their existence from indirect evidence, but you can't prove it definitively. Yet we've made remarkable progress given these limitations. From a few observations, the redshift of galaxies, the cosmic microwave background, the abundance of elements, we've reconstructed the history of the universe back to a fraction of a second after the Big Bang. That's extraordinary. Let's discuss the role of quantum entanglement in the early universe. Entanglement is a phenomenon where particles become correlated in ways that can't be explained by classical physics. Measure one particle, and you instantly know something about another particle, even if they're light years apart. In the early universe, before inflation, everything was close together. Particles were entangled with each other. Then inflation separated them, stretching entangled pairs across vast distances. Today, distant regions of the universe might still be quantum entangled, connected by correlations established in the first moments after the Big Bang. This entanglement might be observable. Some physicists propose that correlations in the cosmic microwave background from widely separated regions could be signatures of primordial entanglement. If found, it would be direct evidence that the universe behaved quantum mechanically at macroscopic scales during the Big Bang. Entanglement also connects to the holographic principle and the idea that information is fundamental. In some formulations, space-time itself emerges from quantum entanglement. The geometry of space is determined by the pattern of entanglement between quantum degrees of freedom. The Big Bang would then be the establishment of an entanglement structure that gives rise to space and time. This is cutting-edge theoretical physics, highly speculative but rooted in serious mathematical work. Physicists are exploring how quantum information theory might provide a foundation for understanding spacetime and gravity. If successful, it could revolutionize our understanding of the Big Bang. Now consider the concept of cosmic variance. When we observe the cosmic microwave background, we're seeing only one realization of the early universe. There were quantum fluctuations during inflation, and those fluctuations were random. We see the result of one particular random draw. This creates an irreducible uncertainty. Even with perfect measurements, we can't determine certain properties of the universe more precisely because we only have one universe to observe. It's like trying to determine if a coin is fair by flipping it once. You get heads or tails, but that single result doesn't tell you much about the coin's true probability. Cosmic variance limits what we can learn about the early universe from observations of our universe alone. Some questions might require observing many universes, which we can't do. This is another fundamental limitation of cosmology. Unless, perhaps, the multiverse is real and different regions of space underwent different inflation histories. Then we might be able to observe multiple realizations by looking at different parts of the multiverse. But those regions are beyond our horizon, so this doesn't help practically. Let's explore the concept of initial conditions more philosophically. Every physical theory requires initial conditions and laws of evolution. You specify where things are at one moment and how they change over time. But where do initial conditions come from? In cosmology, the initial conditions are the state of the universe at the Big Bang. Various theories propose different initial conditions. Inflation proposes a particular configuration of the inflaton field. The Hartle-Hawking proposal suggests a specific quantum state. String theory might predict initial conditions from consistency requirements. But philosophically, positing initial conditions feels arbitrary. Why those conditions rather than others? A truly fundamental theory should perhaps explain its own initial conditions, should be self-sufficient. Some physicists think the ultimate theory will be like that. It will have no free parameters, no arbitrary choices. The laws and the initial conditions will be determined by mathematical necessity. The universe exists in the only way it possibly could, given the laws of logic and mathematics. This is an appealing vision, but it's unclear if it's achievable. Can you have a theory with no free parameters that still accounts for the rich complexity we observe? Or does complexity necessarily require some arbitrariness, some contingent facts that could have been different? These are open questions at the intersection of physics and philosophy. They might not have answers, or the answers might come from unexpected directions. Let's talk about what the universe was like between the Planck time, 10 to the minus 43 seconds, and the end of inflation. This era is almost entirely unknown. Our current theories break down at the Planck scale, where quantum gravity effects become important. We don't have a theory of quantum gravity that's experimentally confirmed, so we can't reliably describe physics at those extremes. But we can speculate. Perhaps space-time at the Planck scale is foamy, constantly fluctuating between different topologies. Perhaps particles as we know them don't exist yet, replaced by more fundamental entities like strings or loops. Perhaps causality itself is fuzzy, with time not flowing in a simple linear way. The transition from this quantum gravitational era to the classical spacetime of inflation is one of the biggest mysteries in physics. How did the smooth, nearly uniform inflating spacetime emerge from the quantum foam? What mechanism selected the particular vacuum state that drove inflation? Why did inflation start when it did? These questions don't have answers yet. They require a theory of quantum gravity, something physicists have been working toward for decades. String theory, loop quantum gravity, causal set theory, asymptotic safety, all are attempts to understand gravity at the quantum level. None has achieved complete success, but each has provided insights. When we finally have a working theory of quantum gravity, we'll be able to probe the Planck era and understand the true beginning of the universe. That might happen in our lifetimes, or it might take centuries. But the pursuit continues, driven by humanity's deep desire to know where we came from. Consider also the inflationary potential, the function describing the energy of the inflaton field. The shape of this potential determines how inflation proceeds. A flat potential gives slow roll inflation, where the field slowly descends and inflation lasts long enough. A steep potential gives rapid inflation that ends quickly. The details matter for predictions about the cosmic microwave background. Hundreds of different inflationary models have been proposed, each with a different potential. Some are motivated by particle physics, emerging naturally from theories like supersymmetry or string theory. Others are phenomenological, chosen to fit observations without deep theoretical justification. Observations have ruled out many models and constrained others. The simplest models, with a single field and a smooth potential, fit the data well. More complex models with multiple fields or features in the potential are less favored but not ruled out. As observations improve, we'll narrow down the possibilities further, hopefully converging on the true theory of inflation. Or we might discover that inflation didn't happen. Some alternative theories explain the observations without invoking exponential expansion. These alternatives face challenges, particularly explaining the flatness and horizon problems, but they remain under investigation. Science requires keeping an open mind and following the evidence. Let's consider black hole thermodynamics and its implications for the Big Bang. In the 1970s, Stephen Hawking and Jacob Bekenstein showed that black holes have entropy proportional to their surface area and emit thermal radiation. This was shocking because it connected gravity, quantum mechanics, and thermodynamics in unexpected ways. The entropy of a black hole is enormous, much larger than the entropy of the matter that formed it. This suggests that black holes represent high-entropy states. But the early universe, which in some ways resembles a black hole turned inside out, had low entropy. How does that fit together? The resolution involves the gravitational field. When you account for gravity, an evenly distributed hot plasma like the early universe actually has low entropy. As the universe expands and cools, gravity causes matter to clump, forming stars and galaxies. This increases entropy. Eventually, black holes form, representing the maximum entropy for a given mass. The universe is on a journey from low to high entropy, from uniform simplicity to complex structure to ultimate dissipation. The Big Bang was the low-entropy starting point, and the far future, filled with evaporating black holes and cold radiation, will be the high-entropy endpoint. This entropic arrow of time is why we remember the past but not the future, why causes precede effects, why we age. It all traces back to the special initial conditions at the Big Bang. Understanding why those conditions were special is crucial for understanding time itself. So where does this leave us? After exploring quantum fluctuations, inflation, multiverse theories, loop quantum gravity, cosmic strings, anthropic reasoning, holographic principles, and countless other ideas, what can we actually say about how the universe started from nothing? Here's what we know with confidence. The universe was once incredibly hot, incredibly dense, and incredibly small. It expanded and cooled. Nuclear reactions in the first minutes created the light elements. After hundreds of thousands of years, atoms formed and light could travel freely. Gravity pulled matter together into the first stars and galaxies. Over billions of years, the cosmos evolved into the structured, complex, beautiful universe we observe today. We have evidence for all of this. Multiple independent lines of evidence, from the cosmic microwave background to the abundance of elements to the distribution of galaxies. The Big Bang theory is not speculation. It's the most well-tested, well-confirmed theory in cosmology, supported by decades of observations. But when we push back to the very beginning, to the first tiny fraction of a second, our certainty evaporates. We enter the realm of speculation, elegant mathematics, and untested theories. We don't know if inflation happened, though it's the best explanation we have for many observations. We don't know what drove inflation if it did occur. We don't know if there was a big bounce, a quantum tunneling event, an eternal multiverse, or something else entirely. And when we ask the ultimate question, why is there something rather than nothing, we reach the boundary of physics. Maybe quantum mechanics makes nothingness unstable. Maybe mathematical structures exist necessarily and the universe is one such structure. Maybe our universe was created by some process in a larger cosmos. Maybe existence is simply a brute fact requiring no explanation. We might never know for certain. Some questions might be forever beyond the reach of science, not because we're not clever enough, but because they transcend the framework of empirical investigation. You can't observe what happened before observation was possible. You can't measure what exists outside the measurable universe. You can't test theories about untestable realms. But here's the remarkable thing. Despite these limitations, we've learned an astonishing amount. A few centuries ago, people had no idea how old the universe was. A century ago, we didn't know it was expanding. 50 years ago, we had barely detected the cosmic microwave background. Today, we can describe the universe's history back to a fraction of a second after the Big Bang. We can measure its age to within 1%. We can map its large-scale structure across billions of light years. This is one of humanity's greatest intellectual achievements. Using mathematics, physics, and careful observation, we've reconstructed our cosmic origins. We've traced the story from a hot, dense beginning to stars, galaxies, planets, and life. We've shown that the atoms in our bodies were forged in stellar furnaces. We've revealed that we're made of the same stuff as distant galaxies, governed by the same laws, part of the same cosmic story. And the story isn't finished. We're still learning, still observing, still theorizing. Every year brings new data from increasingly sophisticated instruments. The James Webb Space Telescope is revealing the earliest galaxies. Gravitational wave detectors are opening new windows on the cosmos. Particle accelerators are probing higher energies, closer to Big Bang conditions. Future experiments will be even more powerful, pushing the boundaries of knowledge further. Perhaps within our lifetimes, we'll detect primordial gravitational waves and confirm inflation. Perhaps we'll discover dark matter particles and solve that mystery. Perhaps we'll develop a working theory of quantum gravity and peer into the Planck era. Perhaps we'll find evidence for or against the multiverse, for or against cosmic bounces, for or against some theory we haven't even imagined yet. Or perhaps some questions will remain open, mysteries for future generations to ponder and investigate. That's okay. Science doesn't promise complete knowledge. It promises a method for progressively better understanding, for refining our models, for getting closer to truth even if we never fully arrive. What matters is that we keep asking, we keep observing, we keep thinking, because the question of how the universe began isn't just academic curiosity. It's about understanding our place in the cosmos, our origins, our destiny. It's about knowing what we're made of and where we came from. It's about grasping the fundamental nature of reality itself. When you look up at the stars tonight, remember that you're looking back in time. The light you see left those stars years or centuries or millennia ago. The faint glow of the Milky Way contains photons from thousands of light years away. And if you could see in microwaves, you'd detect the cosmic microwave background, light from 13.8 billion years ago, carrying information about the infant universe. You're not separate from this cosmos. You're part of it. The calcium in your bones was created in a massive star that exploded billions of years ago. The iron in your blood was forged in a supernova. The oxygen you breathe was produced by countless generations of stars. You are, quite literally, made of stardust, assembled into a pattern complex enough to contemplate its own origins. This is the gift of cosmology, perspective. We live on a small planet orbiting an ordinary star in an ordinary galaxy in a universe containing hundreds of billions of galaxies. We're tiny, ephemeral, cosmically insignificant, and yet we're the universe's way of knowing itself. We're matter organized into consciousness, capable of understanding where we came from and how we got here. That's extraordinary. Out of the primordial plasma of the Big Bang, through billions of years of cosmic evolution, nature has produced beings capable of reconstructing that history. We can look at ancient light and decode the story it tells. We can write equations that describe the birth of time and space. We can imagine and test theories about the deepest mysteries of existence. Whether the universe came from a quantum fluctuation, a bouncing cosmology, a multiverse of eternal inflation, or something we haven't conceived, the fact remains. Here we are, against impossible odds, in a universe fine-tuned or selected or simply lucky enough to permit our existence. We emerged. Hydrogen atoms assembled into stars, stars created heavier elements, those elements formed planets, chemistry became biology, biology became consciousness, and consciousness began asking where it all came from. We don't have all the answers. We probably never will. But we have something perhaps more valuable. A method for seeking answers, a commitment to following evidence wherever it leads, and the courage to ask the biggest questions imaginable even knowing we might not find complete solutions. The universe started from something that looks an awful lot like nothing. A quantum fluctuation, a vacuum instability, a mathematical inevitability, or perhaps something beyond our current understanding. It exploded into existence, inflated faster than light, cooled and expanded, formed matter and antimatter with a slight asymmetry favoring matter, synthesized the first elements, released the cosmic microwave background, collapsed into the first stars, assembled galaxies, enriched space with heavy elements, created planets, and eventually, on at least one planet orbiting one star, gave rise to life and consciousness. And now that consciousness is looking back, retracing the journey, understanding each step, and marveling at the magnificence of it all. We're asking how it happened. We're proposing theories, making predictions, testing them against observations. We're slowly, painstakingly piecing together the greatest story ever told. The story of everything. This is humanity at its best. Not fighting over resources or ideologies, but cooperating to understand reality. Scientists from different countries, different cultures, different backgrounds, working together to decode the universe's secrets. Building telescopes on mountaintops and in deserts, constructing particle accelerators underground, launching satellites into space, analyzing data, writing papers, sharing results, building on each other's work. The question of how the universe started from nothing brings out our deepest curiosity, our most profound sense of wonder. It connects us to something larger than ourselves, to the cosmos that created us, to the long chain of causation stretching from the Big Bang to this present moment. We may never know for certain what triggered the Big Bang or why there is something rather than nothing. Those questions might be forever beyond reach. But we can know the story of what happened next. We can understand how the universe evolved from simplicity to complexity, from uniformity to diversity, from a featureless plasma to a cosmos filled with stars and planets and life. And maybe that's enough. Maybe the true answer to how the universe started from nothing is simply, it did. It happened. And we're here to witness it, to study it, to celebrate it. We're the universe experiencing itself, asking itself questions, seeking to understand itself. That's not nothing. That's everything. So the next time someone asks you how our universe started from nothing, you can tell them the truth. We're still figuring it out. We have theories and evidence and observations that take us remarkably close to the beginning. We can describe the universe at 1 second old, at 1 microsecond old, maybe even at 10 to the minus 35 seconds old. But the very first moment, the origin of origins, remains mysterious. And that's okay. Mystery is what drives science forward. Every answered question reveals new questions. Every solved puzzle exposes deeper puzzles. The fact that we don't know everything yet isn't a failure. It's an invitation to keep exploring, keep experimenting, keep thinking. Because somewhere out there, encoded in the cosmic microwave background or in gravitational wave signatures or in the mathematics of quantum gravity or in observations we haven't made yet, are clues to the ultimate origin. The universe is telling us its creation story. We're learning to listen, and what a story it is. A story that began 13.8 billion years ago with something that looked like nothing and became everything. A story that includes us, explains us, connects us to every star in the sky. A story that transforms how we see ourselves and our place in the cosmos. We are not the center of the universe. We're not even particularly important on cosmic scales. But we are part of the story. We're characters written into the narrative by the universe's own hand. And uniquely, we're the characters who can read the story, understand it, and appreciate its profound beauty. From nothing or something indistinguishable from it came everything. From the Big Bang came space and time. From energy came matter. From matter came stars. From stars came planets. From chemistry came life. From life came consciousness. From consciousness came questions. And from questions comes understanding. The circle completes. The universe creates us, and we understand the universe. The cosmos gives rise to minds, and those minds comprehend the cosmos. Existence contemplates its own existence and asks the timeless question, why? We may never have a final answer, but the search itself is profound. In seeking to understand how the universe began, we're engaging in perhaps the most human activity there is. The quest for knowledge, the pursuit of truth, the desire to know our origins and our place in the grand scheme of things. This is what makes us human. Not our tools or our technology, but our curiosity. Our need to ask why, to search for answers, to push beyond what's known into what's unknown. Every generation builds on the discoveries of previous generations, climbing higher up the mountain of knowledge, seeing further across the landscape of cosmic truth. We stand on the shoulders of giants. Einstein, who revealed that space and time are dynamic, Hubble, who discovered the universe is expanding, Penzias and Wilson, who found the cosmic microwave background, Goose, who proposed inflation, Hawking, who explored quantum cosmology, and countless others who contributed pieces to the puzzle. And we're adding our own pieces. Every observation, every experiment, every theoretical insight brings us closer to understanding. The complete picture may be beyond reach, but each generation sees more clearly than the last. That's progress. That's the scientific enterprise at work. So yes, the universe started from nothing, or from a quantum vacuum, or from a previous universe, or from mathematical necessity, or from something we can't yet imagine. The exact mechanism remains unclear, but what's absolutely clear is that it happened, that it led to us, and that we're capable of investigating and partially understanding it. That's the miracle. Not that the universe exists, but that we can comprehend it. Not that there's something rather than nothing, but that the something includes conscious beings capable of asking about the nothing and figuring out how the transition occurred. We are the universe made conscious. We are stardust contemplating stars. We are matter pondering its own existence. And in doing so, in asking how our universe started from nothing, we're participating in one of the most profound adventures in human history. The quest to understand everything. The journey continues. New telescopes will peer deeper into space and further back in time. New theories will propose novel explanations. New experiments will test predictions we can barely imagine today. The boundary of knowledge will advance, mystery by mystery, discovery by discovery. And maybe someday, perhaps in the distant future, someone will stand before an audience and say, "We know how the universe started. We understand the mechanism, the cause, the origin. The mystery is solved." Or maybe they'll say, "We've learned that the question itself was wrong, that origins don't work the way we thought, that existence is stranger and more wonderful than we imagined." Either way, the pursuit will have been worth it, because in seeking to answer how our universe started from nothing, we've learned who we are, what we're made of, and how we fit into the cosmic story. We've connected ourselves to the deepest truths of existence. We've touched the fundamental fabric of reality. And we've discovered something even more important, that we're capable of such understanding. That the human mind, evolved on an African savanna to find food and avoid predators, can grasp the birth of time itself. That we can take the universe's measure and find it beautiful. That's the real answer to how the universe started from nothing. It started in a way that eventually, inevitably, led to minds capable of asking the question. It began with the possibility of understanding encoded into its very structure. And now, 13.8 billion years later, here we are, understanding. The universe started from nothing and became everything, including us. And we, in turn, are starting from ignorance and approaching omniscience, one discovery at a time. It's a journey without end, a quest without final destination. But every step forward is a triumph, every answered question a celebration, every glimpse of cosmic truth a moment of transcendence. This is why we do science. This is why we build telescopes and accelerators. This is why we spend our lives studying equations and analyzing data. Because the universe is knowable and we are the knowers. Because existence is a mystery and we are the mystery solvers. Because there was nothing and now there's everything and we get to figure out how that happened. What a privilege. What a responsibility. What an adventure. The story of how our universe started from nothing is still being written. We're the authors now, adding chapters through our observations and insights. And though we may never write the final chapter, though the ultimate truth may forever elude us, we can be proud of how far we've come and excited about how far we'll go. From nothing to everything, from the Big Bang to this moment, from the first quantum fluctuation to the consciousness that contemplates it. The journey is the answer. The search is the discovery. The question itself is what makes us human. How did our universe start from nothing? However it happened in a way that made this moment possible. You, reading or hearing these words, thinking about cosmic origins, participating in humanity's greatest intellectual quest. That's the real miracle. That's the answer worth celebrating. The universe exists. We exist within it. We can understand it. And in understanding, we become more than we were. We transcend our tiny corner of space and time. We touch infinity. We grasp eternity. We participate in the cosmos at the deepest possible level. From nothing came everything. From everything came us. From us comes understanding. And from understanding comes wonder, gratitude, and the determination to keep asking, keep seeking, keep exploring until we know all there is to know about this magnificent, mysterious, impossible yet actual universe we call home. That's how our universe started from nothing. It started beautifully, continues beautifully, and we're here to witness and comprehend the beauty. What more could we ask for?